start a discussion of triple integrals. I just want to remind you what they are. They're just like double integrals, really, with one more dimension, so they're not too hard. It's not imperative that you understand everything here. You just want to understand the concepts, you know, when you can apply these triple integrals. A triple integral over b, for box if you like, where x goes between x equals a and x equals b, y goes over this interval cd, and z goes over this interval pq. These are Cartesian products, so this is the rectangular box in three-dimensional space. X, y, and z going between those coordinates. Here it is, a to b, c to d, and p to q. What does the triple integral mean? Well, we'll make this definition of the triple integral over the box B of a function f of x, y, z dv. This notation means the limit as the number of boxes n goes to infinity, where I've broken this up into m, n, and p subintervals, and little n is n times p. That's the whole total number of boxes. And I sum in the fourth dimension, if you like, f of xi star, yj star, zk star, any point in the ijk box, times delta v n, this is sometimes called, with n indexing the boxes, where the width of the nth box is delta xi, the length is delta yj, and the height is delta zk. And so this is the ijk volume multiplied by the fourth dimension gives you sort of a four-dimensional volume of the ijk box, and then you sum over all those boxes and you get a volume in four dimensions. What good does that do? It's not real, right? Well, actually these have real applications, as you'll see, because if instead of thinking f of f as a fourth dimension, you think of it as a density, you take the density at some intermediate point in the box times the volume of the box, you get the approximate mass of the ijk box, right? And if you add those up over all the boxes, taking real small boxes, this gives you an estimate of the mass of the total object broken up into all these small boxes. When you take the limit as n goes to infinity with mass density f over some solid, this gives you the mass of the big box that's been broken up into all these sub-boxes. Alright, so that's the definition and the motivation for it. It doesn't have to be mass density, it can be charge density, and you get the charge enclosed in the box, or some other density function. Now, Fubini's theorem for triple integrals says that, just in analogy to what we had for double integrals, if you have a triple integral over a box B of a function f of x, y, z, thought of as a density of some sort, or you could be, if this is a fourth dimension, be computing as a mathematician a four-dimensional volume. You can integrate, you can evaluate this thing. Who wants to do the limit of the sum, right? As a triple integral. In which you integrate first with respect to x, a partial integral, holding y and z constant, and then you integrate with respect to y, a partial integral holding just z constant, and we call these iterated integrals, and then an integral with respect to z, just an ordinary integral from p to q. And you don't have to do it in this order. Actually, there's 6 different orders you can put these integrals, and all 6 of them work, where you let each integral, for x goes between a and b, because that was the position along the x-axis you went over. Y went between c and d, and she put that on the y integral, and z goes between p and q. So it's completely analogous to Fubini's theorem for 2 dimensions, except now you have 6 different orders of integration and 3 different variables. So suppose, just as an example, I want to compute the mass of the box, where x goes from 0 to 1, y from -1 to 1, and z from 0 to 2. And box has this density, e to the 2x plus y plus z. The mass grows exponentially as you leave the origin there. And what do, I say, well, the triple integral, the mass is the triple integral of the box, integrates between these endpoints, right, 0, 1, minus 1 to 1, 0 to 2. The density function, dx, dy, dz is off the page there. And when you evaluate the inside integral with respect to x, you treat y and z as constants. So this is e to the 2x plus k1 plus k2. Its integral is e to the 2x plus k1 plus k2 over 2. And you evaluate it at 0 and 1 using calculus 1 techniques. This becomes e to the 1/2 e to the 2 times e to the y plus z is still there. Evaluate at the top endpoint, and then evaluate at the bottom endpoint, you just get e to the 2 times 0 is 1. And so this is, the e squared times this is evaluating at the top endpoint, and 1 times this is evaluating at the bottom endpoint, and then you subtract them. That's what's in there. And now you have an integral that involves only y and z, and you integrate that, here, y and z. You integrate that with respect to y and get, well, this is just a constant. You can pull it out. And e to the y plus z integrated, treating just z as a constant, becomes, well, integral e to the y is e to the y. And so I think that this is e to the y times e to the z, and integral e to the y is e to the y. This has to be evaluated at the two endpoints and take the difference, and you get e to the 1 minus e to the minus 1 when you do that. And then e to the z is left in the integral. You integrate that by calculus 1. Integral e to the z is e to the z. Plug in the two endpoints and take the difference, you get e squared minus 1. And so the mass of the box is this, 1/2 e squared minus 1, e minus e to the minus 1, e squared minus 1. The total of e squared minus 1 cubed over 2e is the total mass of this box. Well, that's good for boxes. Maybe we can do one more of these, huh? Once again, let's see. That's the wrong one. This one. Suppose I want to take the triple integral of x plus z over a box. And suppose the box goes with x between 0 and 1, y between 0 and 2, and z between 0 and 3. We do this inside integral first, treating y and z as constants. And here's a trick that comes up sometimes. Since y isn't appearing in here, this integral is just going to come out to be a function of z, right? You integrate with respect to x and evaluate it at the endpoints, the x goes away. And then you got z in here, but y isn't present, so all this is a constant. You can pull the dy out here and just integrate with respect to y by pulling this constant out here. So you've got integral dy just going from 0 to 2 is easy, and then you've got the double integral here that's left. Now this double integral just treats z as a constant on the inside, and integral of x is x squared over 2, integral of z is xz, doing partial integrals. You plug in the endpoints and take the difference. You get 1/2 plus z, and then that needs to be integrated through calculus 1 with respect to z. Just an ordinary integral gives us 1/2 z plus 1/2 z squared. Plug in 0 and 3 and take the difference. We wind up with 12 kilograms if this is say density in kilograms. All right, so there's a couple of examples. Now, more generally, we don't want to just deal with boxes, we want to deal with spheres and cones and all sorts of other three-dimensional objects. How do we integrate over a more general three-dimensional object? Well, we embed that object, maybe it's an ellipsoid or some sort of big oval here. We embed it inside of a rectangular box, just like we did for non-rectangular regions of the plane when we wanted to do a double integral. Similar in triple integrals, we embed in a rectangular box instead of a rectangular plane region. And within here, we take the integrand, f, which might be a density or something, and replace, when we do this integral over the boxes, take width times length times height times f at an interior point when the point in the box is inside the original region, but we put f hat equals 0 when we're in one of these rectangular regions and the point is not in the original region. So we do that same kind of thing. We replace f, the integrand, with f hat that's equal to f when you're inside W, the region that's an oval here, and it's equal to 0 otherwise, and we take the limit of the triple sum of f of x star, y star, z star hat over the region, adding up numbers when we're inside the region W and adding 0 when we're outside. That's the triple integral. Its definition, I won't go into all the details there. But then there's this nice theorem for evaluating it. In order to evaluate such a triple integral over a non-rectangular region, which is the limit of a triple sum, just like the other one, it's just that sometimes you're adding 0 and sometimes you're adding not 0. You can evaluate the double integral over the region below that's its projection. So you have a projection of W that's R, shaded plane region here, and you take the double integral over the projected region of the xy plane of the partial integral going from the bottom surface, z1 of xy, to the z equals z1 of xy to the top surface, z equals z2 of xy. And this iterated integral, in which the inside integral is a partial integral from the bottom surface to the top surface, and the outside integral goes over the plane region of projection, we'll evaluate the triple integral. That's how you actually do it, since you don't want to add up the limit of the sum. So suppose we want to do this one. Suppose we want to evaluate the triple integral of x dv, and now it's over a solid W that's a tetrahedron here. It's a four-sided figure with 4 triangular sides, and it's the region in the first octant, right? 3 spaces broken up into 8 octants by the 3 coordinate planes. If you're in the region where the x, y, and z are all positive, we call it the first octant. If z is positive, and if you rotate around here where x is negative, but z, y, and z are still positive, that's the second octant. Then third, and then fourth, staying over the xy plane. And that corresponds, if you look down to the quadrants, 1, 2, 3, 4, right below them. And then if you're straight below octant 1 with z negative, then that's octant 5, and then octant 6 is below octant 2, octant 7 below octant 3, and octant 8 below octant 4. Maybe I should draw that just to be. So octant 1 is up here, above the xy plane, and here's xy plane, here's the xz plane, and then here is the xz plane. And if you're in this first part here, where all 3 coordinates are positive, there's octant 1, and octant 2 is back here, octant 3 is back here, octant 4 is up here, all above the xy plane, with octant 5 down here, 6 down here, 7 down here, and 8 down here, in that order. All right. Now, what does our theorem say about evaluating this triple integral over the tetrahedron, it's a big hint to draw a picture, right? So make a sketch of these things always. If you know it's below the plane, x plus 2y plus 2z equals 2, which I know is a plane, right? It's ax plus by plus cz equals d. So it's a linear equation. A linear equation in 3 dimensions is a plane, right? We can sketch that. An easy way to do that is to find the intercepts, right? We mentioned this. Try putting 2 of the coordinates equal to 0, say. Let's put x and y equals 0, then we have 2z equals 2, so z has to be 1. We get the point 0, 0, 1 is on the plane. We can plot that. It's easy because it's on an axis, right? If we put x and z equals 0, we get 2y equals 2, and y equals 1. So we get the point 0, 1, 0 on the y-axis. If we put y and z equals 0, we get x equals 2. 2, 0, 0 is a point on here. We'll plot those 3 and draw those triangles, how people often draw a plane region in the first octant like that. Now we have to figure out the projection. Well, it's easy because it's the plane region right below here. It's this triangle, right? We'll call that R. And in order to evaluate this triple integral, we will do a double integral over the triangular plane region in xy space, R, of the integral from the bottom surface, well, that's just z equals 0 is the bottom, so I put 0 down here, to the top surface. I have to solve this for z. I write this, it's hard to see here, isn't it? Let's try it again. Too much. All right. We solve this equation for z and get z equals 1 minus y minus a half x when we solve this for z. So the top surface being z equals this, we integrate from 0 to this, right? That's the theorem. We integrate the integrand for that, and then outside is the double integral over the plane region, that's the projection. All right. Now, if you do the inside integral of x with respect to z, x is treated as a constant, so the integral is xz. This has to be evaluated at the top endpoint and the bottom endpoint, take the difference, right? It's partial integral with respect to z, treating y and x as constants. And so I plug in this for z, and this for z, and take the difference. And the bottom produces 0, but the top produces x times 1 minus 1 half x minus y. Now I have to do this double integral of the plane region. That's what we already did in the other section. It's easy now, right? We just apply the vertically simple region, or type 1 region, we call it in the book, to the double integral. We integrate from the minimum value of x to the maximum value of x, bottom curve to the top curve, right? Here's the region R in the xy plane, right? We can integrate from the minimum x and maximum x between this curve and this curve. What's the equation for the top curve? That's always a tough question. What you do is you look at the points. It goes through 2, 0, and 0, 1. You can use the 2-point formula to deduce the equation for the line. I prefer, for speed, I find, to use y equals mx plus b, and where m is the slope and b is the y-intercept. What's the y-intercept? It's 1. What's the slope? Well, I went down 1 over 2, so the slope is minus a half. So this must be the line y equals minus a half x plus 1, right? It's the slope times x plus the y-intercept. Y equals mx plus b. So I'll put that in now, and for the double integral, I go from the bottom curve, y equals 0, to the top curve, y equals 1 minus a half x. X going from its min to its maximum value, 0 to 2. I can do this, right? And I have this integrand, which is multiplied out, x minus xy minus a half x squared. Well, this is a lot more clumsy terms, but it's actually an easy problem. We integrate this one, partial integral treating x as a constant, get xy, right? Integral of x is xy. Integral of minus xy is minus a half xy squared, because x is treated as a constant. Integral of minus a half x squared is minus a half x squared times y. We're going to have to plug in these 2 endpoints and take the difference. We plug them in, and there's some details left out, but you wind up with 3/5. you can see even for these simple polynomials, these things can get complicated. So switching to a coordinate system which solid has an easy presentation is actually important in some of these things. Sometimes you can get these quite complicated. If it's got a radial symmetry, you might go to polar coordinates. We're going to do that next time. Well, here's one last picture here. Suppose we wanted to do this triple integral, which is hiding pretty well up here. Let's see if I can get it big enough so we can read it. There it is. I should say we should do these in reverse. If somebody gives you an integral, you can sketch the solid whose volume it is. Suppose I had the integral from 0 to 2, integral from 0 to 2 minus y, integral from 0 to 2 minus x minus y, dz, dy, dx. Well, remember our formula. This must be the bottom surface, z equals 0. This must be the top surface, z equals 2 minus x minus y. What kind of surface is that? It's a linear equation. It has to be a plane, right? It can be written as ax plus by plus cz equals d. So I sketch the plane. I can do the same thing with the intercepts I did last time. I can say, well, if this is z equals 2 minus x minus y, then I can put xy equals 0 and I get z equals 2. So I plot 2 here. If I put x and similarly, if I put x and z equals 0, I get y equals 2. Put y and z equals 0, I get x equals 2. And so these 3 points all are on the plane, and I sketch the plane. Then the bottom surface is z equals 0. And I say, well, now what is this plane region when x goes from 0 to 2 on the x-axis and y goes between in the plane between 0 and 2 minus y. This is the plane of projection here that we're looking at. And it's this plane right down here. X goes from 0 to 2. We're looking in the xy plane. X goes from 0 to 2. Y has a minimum y equals 0 and a maximum y equals, x is in the middle. Y goes from 0 to 2. That's the outside variable. Outside variable goes between fixed endpoints 0 and 2. These should always be numbers on the outside. And the inside variable x goes between x equals 0, which is this one, and x equals 2 minus y, which is this one. Kind of tricky in this problem, huh? So x equals 2 minus y is a line, right? It's a x equals my plus b equation. And you just plot its 2 points here and sketch it. And then x equals 0 is this line. And so you infer that the region of projection is this triangle. And you're interested in the volume below this plane, z equals 2 minus x minus y that we sketched with 3 points. And over the xy plane, y z equals 0. Over this little triangle. It's this tetrahedron problem again. There it is.